Soap is one of those things we use every day, hopefully, but usually don't think about how it does its job of removing dirt, germs, or anything else we don't want on our hands. Soap actually works in two ways. First, it both repels and attracts water. This might sound like a contradiction, but it's actually not. Soap can be made of any number of different things, so it's impossible to give one formula for soap, but the soap molecule is usually depicted looking something like this. The soap molecule has a head and a tail. The tail of the molecule is hydrophobic, or repelled by water. Hydro meaning water, and of course phobic being a word we most commonly associate with meaning a fear of something. But in chemistry, it simply means repelled by or lacking a chemical affinity. It's all just a fancy way of saying that the tail of the soap molecule doesn't mix with water. Now, the head of the molecule is hydrophilic, with the suffix philic meaning attracted to. So part of the molecule is attracted to water, and part of the molecule is repelled by water. The nifty thing here is that the hydrophobic tail tends to be attracted to other things that are repelled by water. See, you're oily. Okay, that's not an insult, though it can sound like one. We're all oily. Our skin produces an oil called sebum that is responsible for keeping our skin from drying out. This is a good thing because overly dry skin can crack and bleed, causing the barrier our skin provides to no longer be able to keep germs and bacteria from entering our bodies. But it also means that water can't really do much to clean our hands. We've all heard the saying, oil and water don't mix, and well, it's true. Water will just slide right over the oily barrier on our skin without doing much of anything. And here's where soap comes in. The hydrophobic tail of the soap molecule is attracted to oil. So our skin oils will bond with the tail of the soap molecule while the water bonds with the head of the molecule. As you rinse the water away, the oil and any foreign matter caught in the oil will rinse away with it. And on top of that, once the oily barrier is broken up, any foreign matter not stuck in the oil will tend to either just bond with the water or with the tail of the soap molecule if that foreign substance isn't attracted to water itself. Now, to keep things simple, I've talked about one common thing we do with soap, and that is wash our hands. But all of this is true for other common uses of soap, such as taking a shower or bath. Shampoo is just another type of soap specifically made to work with hair. But what about washing other things like the dishes? Basically, it works the same. Many foods will leave behind oils as well. But some foods are greasy rather than oily. Remember how I said that the tail of the soap molecule tends to be attracted to other things that are repelled by water? Well, grease doesn't mix with water any better than oil, but it will mix with the hydrophobic tail of the soap molecule. So basically, the same thing happens. You're just substituting grease for oil. And the only real difference between hand soap or body soap and dish soap is that dish soap is made to be more effective at breaking up and mixing with grease than hand soap is. If all you have is hand soap and you need to wash a dish, you can. Hand soaps just are not specifically optimized for the purpose, and you might need a bit more soap and elbow grease to get the job done. But at the molecular level, the same thing is going on. Now, at the beginning of the video, I said that soap worked in two ways. The other thing that soap does is simply break up the surface tension of water. We learned early on in school that water is H2O, or two hydrogen atoms and one oxygen atom. The molecules in water are held together by what is called a hydrogen bond. The positive charge of the hydrogen atom is attracted to the negative charge of the oxygen atom. Now, Without getting too deep into it, this video is about soap after all and not hydrogen bonds. The short of it is that those two hydrogen atoms in the water molecule will look to bond with other oxygen atoms. If those oxygen atoms have already formed a molecule of water, they'll still bond together, but you'll have surface tension. Surface tension is why belly flops hurt, or why water will beat up on a windshield. The molecules of water want to stay together. So if this picture is a surface of something we wish to clean, magnified to the point that we can see it start to look a bit like a mountain range, and the red ball represents something we want to remove, we would have trouble getting to it. Because of the surface tension of water, if we added water, it would simply do something like this. We can see that we're not going to be able to get to the red ball this way. The surface tension just won't let us. But thankfully, soap is also what is called a surfactant. A surfactant is a substance that lowers the surface tension of a liquid. So when added to water, soap will loosen the bonds between the molecules, and instead of simply flowing over any valleys in our surface here, they will fall right in and get to the red ball. At this point, the soap and water can simply physically knock it out of there and take it along for a ride and off of the surface we want to clean. So in those two ways, soap helps us to clean. Usually it's going to be a combination of both that help us get rid of all the grime and bacteria and whatnot off of our hands or dishes or whatever. But hopefully you now have a greater appreciation for just what happens when you use soap and why soap is such a vital thing in our everyday lives. Thanks for watching. I hope you enjoyed that video. This is only my third video, so hopefully it's better than my first video and my second video. But I know I'm still new to this, so the videos aren't going to be all that great yet. But if you like this type of content and want to help someone who's just starting out, I hope you like, comment, and subscribe. Until next time, this is Random Knowledge. Thanks for watching.